Right, so this is a required practical video, specifically the forces and elasticity one. So we need to know some key terms first. So an elastic object is one that returns to its original shape when the force that causes it to change shape is removed. So this elastic band is a perfect example. The thumb puts a force on the band, makes it change shape. When the thumb is removed, the band goes back again. So we call that elastic deformation. Then we've got this bubble gum. We know that if we stretch bubble gum, it doesn't return back to its original shape when you remove the force. So we call that inelastic deformation. It does not return to its original shape when the force is removed. Now, this is basically a method for what we do for the required practical. So run through it, make sure you remember it. You've all done this before. This is just revision. So we've got data in the table from example of a student completing the investigation. We have to use this data in our method. Okay, so we've got a force is going up in twos, and they hang these weights, which represents each of these forces, on a spring, and that shows how much the spring is extended by. So here is an example of a diagram you could draw in your exam, and it needs to be labelled whenever you draw a diagram. So we've got a boss and a clamp which hold the spring. We've got the spring itself. We've got the mass and hanger, which causes the spring to extend, and we've got a ruler to measure the extension. Now, this is the sort of thing you could write as a method. Set up the apparatus as shown. Ensure the start of the ruler is aligned with the top of the spring. So start of the ruler aligned with the top of the spring. Measure the original length of the spring with 0 newtons on it, and then carefully hang a 2 Newton weight on the spring. We're starting with 2 newtons because that's what it said in the table. Measure the new length of the spring, and then work out the extension by doing the stretch length minus the original length, so the difference as they've put there. Repeat steps 1 to 5 for 4 newtons, 6 newtons, 8 newtons, and 10 newtons. We're using those because that's what's in the table. If you're not given a table, I would just go up in ones. So causes of inaccuracy, because it said your answer should include any cause of inaccuracy in the data. So holding ruler, so not fixing it in place. So what you could do is move the ruler about, not measure it properly. That would cause it to become inaccurate. Ruler not vertical. So if the ruler's not vertical, it's going to measure a longer length than it actually is, a longer extension than it actually is. And then reading off a ruler not at eye level. So we call this the parallax error. So whenever you read off a ruler, you must be at the same level. The eye must be at the same level. So if you're reading there, your eye should be at that level here. Now, these are the sorts of questions that you could be asked. It says the student measured the extension for 5 different forces rather than just measuring the extension for one force. Suggest why. So if we go back, we can remember 5 different forces. So to identify any anomalous results, so if we only did one example, we wouldn't know whether our first measurement we did was anomalous or not. We have to do numerous ones to check they fit the pattern. To reduce the effect of random error. So again, we wouldn't know, if we only did it once, we wouldn't know whether that first one was an error or not. We have to do it lots of times to see whether the first one fits the pattern or not. Now, all you've got to do here is fill in the graph. So we'll do that dead quick. 2 points there, 1 and 2, and then do a line of best fit. Clearly, this is a straight line of best fit. And then you'll get this equation on your equation sheet. Just look for an equation with extension, force, and spring constant. And we've got that there. Now we need to use that equation, okay, on the next question. Before we do that, I want to explain something different as well. Sometimes if we plot a spring, we get a line that starts off straight and then it becomes curved. At this point where it becomes curved, we say that the spring has reached its limit of proportionality. So often you're asked to mark when does the spring reach its limit of proportionality. And basically you mark on the graph where it starts to curve, which is here. And if the line has reached its limit of proportionality, we say there's too much force on the spring and it will not return to its original shape. So this was the spring originally. We put too much force on it. It doesn't go back to its original shape. It causes a line to curve, and we call that the limit of proportionality. Next, we use our equation from before to work out this. Okay, so we've got this data in the table, so we just use the data in the table here. Now it's easy, you could use any of these rows, but I would use the numbers that were easier, 10 and 20. But remember, these are in centimeters, so to get to meters, we need to divide by 100. So we go back just here, and the first thing we do is get our extension that was 20 centimeters. We divide it by 100 to get 0.2. That gets us 1 mark. Then we put that into the equation, just there, and we get our 10, which was our weight or our force, and we divide it by 0.2, which I converted, gives us 50. And the spring constant is newtons per meter, so the answer is 50. Now it says here, Hooke's law states the extension of an elastic object is directly proportional to force applied, provided the limit of proportionality is not exceeded. The student concluded that over the range of forces used, the spring obeyed Hooke's law. Explain how the data supports this. So you go back to your graph, you see that the line is straight and it passes through 0, 0. That means it's directly proportional because it's straight and goes through 0, 0. So that means it does match the student's conclusion because he says that it is directly proportional. So you'll get the marks for saying the line is straight and passes through the origin or 0, 0. And that's everything. Thank you very much.